We're going to call that the heat of solution. Now, by definition, so here's the boring book definition, it's the difference between the energy required to separate the solute and solvent parts and the energy released upon the formation of these ion dipole interactions. And when that solvation process provides more energy to separate the solvents than you need to separate the solvent-solvent particles, the heat of solution is overall negative. It gives off energy. It's exothermic. Yeah, I know that didn't mean much to you at all. So here's some examples. Now this can go both ways. These heats of solution can be exothermic or endothermic. These ammonium nitrate-based cold packs are an example of an endothermic one. In this case, you're making an ammonium nitrate solution, and when you do that, it actually dissolves. Now, in some cases, you also have some cases where the solution gives off heat. Calcium chloride is an example of that. When calcium chloride dissolves, it actually gives off quite a bit of heat. So let's talk about the energetics of that process in cartoon form, because I like cartoons. All right. Now, this is one of the great truths of the universe that we find ourselves in at this time, that Mother Nature is a lazy slob. And this is going to be the driving force of how things dissolve. So we're starting down here. Where you've got the solvent still, let's say this is water, not separated from each other yet. And you have a example solid solute that has its very strict crystalline order here. All right. So let's break this process up into a couple of hypothetical steps. The first one is I'm going to separate the solvent molecules from each other. So this is like, overcoming the hydrogen bonds in water to separate them. And at this case, hypothetically, we haven't done anything to the solute yet. And that's actually the next step. The next step, we're going to bust apart the solid solute. Now, both of these required energy to do so. So in all of these cases, we were overcoming an attractive interaction that's going to require energy. So we had to put in energy to get the solvent apart and then put in more energy to get the solute apart. This is not necessarily to scale. And so the next thing that we do is we combine the solvent and the solute and let them interact with each other. And that, by definition, is going to be downhill energetically. Now, in this example, the resulting energy of the solution ended up being lower than the original energy of the solute just by itself, and the solvent just by itself, and the solute by itself. So even though we had to put in energy for these two steps, we got more back in the solvation step. And that energy difference here is the heat of solution. Now, it doesn't always necessarily work out exactly that way. In some cases, so this would be something like calcium chloride is an example of this. And that's an A. All right. So overall, this process is exothermic. Sometimes it works out like this. So we start with our aggregated solvent and our aggregated solute. We separate the solvent. We separate the solute. We make the solution. So we allow the solvent and the solute to interact. Those are likely attractive interactions. It's energetically downhill, but maybe not enough to get you below the original solvent and solute level. And when that's the case, the heat of solution is going to be endothermic in this case. And so overall, this particular process is endothermic. And this, as an example, would be dissolution of ammonium nitrate, which is what the cold packs are based on. So then you might ask yourself, how does that work? So the previous example worked on the fact that Mother Nature is lazy. Energetically, you want to go downhill. So things that are processes that lower the energy of the system tend to be spontaneous. Not always, but they tend to be. In this particular example, what makes this work is the slob aspect of it. And so what makes this, now mind you, this process is quite spontaneous, but it's still endothermic. And the reason why it works out that way is something called entropy. So entropy is a word that scientists use. It's actually a quantification of disorder. And nature, so spontaneous system, processes that lower the energy of a system tend to be spontaneous. The other thing that can make something spontaneous is an increase in disorder, because Mother Nature is a slob. All right, so disorder is favorable. Nature tends to favor more disordered states. Processes that result in an increase in disorder tends to be spontaneous also. So if you look at, in particular, our solid sodium chloride here, this is highly ordered. And scientists tend to talk about things in terms of disorder. So the solid especially would be low disorder, and here this would be high disorder when you have all that stuff randomly distributed in the solution. And we'd also call this a high entropy state. And as an example, that this is an example that shows you that disorder can drive a process that has no energetic change whatsoever. So this cartoon here is an example of that. And so we're going to call this ordered, because all the helium's on one side, all the argon's on the other, and it's closed. Now, I will say that helium and argon have no significant, in the gas phase, have no significant interactions to each other or to themselves. That's why they're gases. So if you were to open these containers up, so a valve is closed here, the valve's open on the right side, you would find that spontaneously these two would mix. Even though in this particular case, ignore that, there's actually no change in energy, going from here to here, but there is a significant increase in disorder, which is why the process is spontaneous in the direction it shows. What you would never ever observe is the mixture separating back into each other in this case. So disorder can be a very powerful driving force in nature. So let's hit the bullet points for entropy disorder. So it is a measure of the tendency for matter to become disordered or random in its distribution. And so it's a recognition that matter spontaneously changes from a state of order to randomness unless there is some energy that opposes it. And solutions form, and because the solution tends to be much more disordered or disorganized than the solvent and the solute by themselves.